Alright, Calc students, this is video solutions for the with calculator practice test. And you can expect to see about half the problems are going to actually use calculator. We'll see. So here is one without calculator. Function f pictured here. We got, sorry, f is not pictured here, f prime is pictured here, and they want to know on which of the following intervals is the function f is increasing. So f is increasing when the derivative is positive, and this is the derivative, it's positive here and here. So that's answer choice D. If you happen to choose where is it increasing, and you're like, oh, here and here, that is the kindergarten answer. That is not correct, and nobody is ever going to ask you that question. It's just like, when is it going up? Oh, when it's going up. Nobody wants to know if you can do that. So don't be that person who picks that answer. Dy dt is equal to this. By how much does y change as t changes from here to here? So if we have a rate, the integral of a rate gives us the amount of change of the actual thing. So this is just an easy little integral problem. So the integral of that dt is equal to y of 6 minus y of 1. And they're asking how much does y change. So they just want that whole thing. How much should it change? So I just need to put that in my calculator. Let's do it. Sorry. There we go. All right. Let's clear that stuff out and put this. Actually, we can just do this on the home screen. I'll just do math 9 from 1 to 6 of this 6 e to the negative 0.08 times x minus 5 squared. That looks good. Oh, there we go. All right, number 78. Some function has the property that the limit as x approaches 1 from below is positive infinity. So that means approaching 1 from below means like this way is positive infinity. So that's wrong. That could be a contender. This could be a contender. That could not. So it's one of these. 1 from above is negative infinity. Okay, so both of those are good there. As x approaches negative infinity, it's got a horizontal asymptote at 2. That's looks good here, but not here. This is horizontal asymptote at negative 2. So that's this. Just understanding the language of limits there, I guess you could say. Way back to chapter 2 there. 79. Tara's heart rate during a workout. Her rate is modeled by this function h of t, where that's measured in beats per minute. So this h function is her heart rate. Which of the following expressions gives her average heart rate from that to that? So we want to actually find the average value of this. So to find the average value of a function from a to b, you find the area and you divide by how wide the interval is. That's in section 7.6, if you wanted to go back and review any notes or anything. So that in this problem is here. I guess maybe if you were a little bit confused about the whole rate thing, it's possible that you could be tempted to take that, but the h function is her heart rate, and we want her average heart rate. So we want the average of heart rate, and that is what the h function is. So we don't need to be taking its derivative there. Number 80, function has derivatives of all orders using the third degree Taylor polynomial for what's the approximation for 2.1? Okay, so for a third degree Taylor polynomial, x equals 2, that's f of 2, this is just the recipe. You could call this T3 of x if you want for a third degree Taylor polynomial, plus f of f prime of 2 times x minus 2 plus f double prime of 2 over 2 factorial times x minus 2 squared plus f triple prime of 2 over 3 factorial. There you go. So that's just the recipe for making a Taylor polynomial. Now we just need to plug in the stuff and see what we get. So f of 2 is negative 1. F prime of 2 is 4. And we're finding it at 2.1. So 2.1 minus 2, every time that's just going to be a 0.1, like that. And then the second derivative is 6, divided by 2 factorial is 3 times 0.1 squared. And then the third derivative is 12 divided by 3 factorial. 6 is 2 times 0.1, whoops, cubed. So actually I don't really need the calculator here because these are just all decimal places, aren't they? Like this is negative 1 plus 0.4, and then that's squaring that, moves it to the hundredths place. And then that, so it's what, negative 0.568. Of course, you can use your calculator, it's fine. Just showing off. Number 81, looks like more calculator work. F be a function with a derivative given by this. What's the length of the graph from here to here? So the length of a curve, this is just knowing the formula from A to B. Looks kind of like the Pythagorean theorem. Right, remember the parametric one, length of path, or total distance traveled, is square root of dx dt squared plus dy dt squared, and this comes from that. At least I think about it that way. So I've already got the derivative there. So let's see, that's integral from 0 to 1.5. The square root of this squared is just that, what's under there. So you could simplify this or not, but that does simplify to this when you have the 1 plus this thing squared. So let's do that. We could actually do this without well, maybe we could do that without a calculator. Maybe not. We're going to use our calculator anyway. So math 9, going from 0 to 1.5, the square root 2 plus x squared dx. And that looks like 2.470. Uh-oh. Trouble. That is not any of the answers. It's close to that one. Let me just check to see. Oh, that's x cubed, not x squared. Oops. So I bet it's that one that is close to this. Let's do that and see if we can make that a 3. There we go. Sure enough. Crisis averted. All right, got some slope fields here. let h be a continuous function of x, which of the following could be a slope field for a differential equation of the form dy dx is equal to h of x. So h is a continuous function which could be a slope field. All right. So let's think about what this is saying now. If h is continuous, then the antiderivative of that, let's see, we have no jumps, no vertical asymptotes, and no holes to what we are looking for. So I think that if h is going to be a function, then we can't have, if you imagine what the solution curves look like, the things like this and this are, and this are what we call like inhomogeneous differential equations. What that means, if we want it to be a continuous function of x, then that's got to be like dy dx equals only stuff going on with x here. So that means if it doesn't depend on y, that means that when you pick an x value, you have to have all the same slopes. And that is only true of this one. That's an interesting question. I don't remember ever seeing one particularly similar to that. But if this side, if it only depends on x, then we would just get these like stacked family of curves, not the ones that are these. This is like the opposite. This would be like a function of y, right? With all these rows that are the same. And then these ones would depend on x and y. So you can see how it changes in both directions. So, interesting. Let f be a function defined above. K is a positive constant. For what value of k is, if any, is f continuous. So it's only going to be continuous if we get the same thing when we plug 3 into both of those. And just to review real quick, if you object to plugging 3 into this one because it doesn't have the equal sign there, remember we're trying to link up the closed portion of the curve that ends in a closed dot and the open part. If it's continuous, then those two things have to link up like this. That's why we're plugging 3 into both. So let's go ahead and do that. 3 plugged into this. 3 plugged into this. And then however you want to solve this, I think either get everything on one side, set it equal to 0 and graph. I think that's probably what I would do. Or you can graph both of those and see where they intersect. Whatever you like. Let's do it my way. So k cubed plus 3 minus, going to make a little fraction here that looks real nice, just like this, 16 over x squared minus 3. And I need to see where that crosses. It looks like if it does cross, my numerical answers are between 2 and, well, let's say 0 and 10. So make my window reflect that set of choices. And I'm interested in where it crosses the axis. So from -1 to, as long as it goes from negative to positive, I should be able to see where it crosses just fine. Boom. There it is. So very close to 2. That looks like A. If you want to be sure, you can find that 0. And it's between, well, it's between 0 and 10 anyway. I'm going to do 0 and 4 as my left bound and my right bound, just to have a comfortable interval there, and you can see there's our answer. So that's A. Number 84, let f be a differentiable function. Figure above shows the graph of the line tangent to the graph of f at x equals 0. So the function looks like maybe like this or like this. Of the following, which must be true? Is f prime of 0. Well, f prime of 0 is -2, right? Because if this is the tangent line, the slope of this tangent line is -2. So f prime of 0 is -2. Is that equal to negative f of 0? No, it's equal to f of 0, right? Because 0, comma, if this is the tangent line at 0, it actually has to graze the function, like it has to share that point in common with the function. So f of 0 is also -2. So they're equal to each other. That's C. Right, that seems pretty easy. A referee moves along a straight path on the side of an athletic field. Velocity is given by this, t measured in minutes, and v of t is measured in meters per minute. What's the total distance traveled between 2 and 6? So remember, total distance is the integral of speed. And speed in one dimension is just the absolute value of velocity, and in 2D, speed is the Pythagorized components of the velocity, right? It's that magnitude. So either way, you got to find the integral of one of these expressions. This is just one-dimensional, so it's just this. So I'll set up my integral in my calculator here. It's Math 9, going from 2 to 6. And absolute value of this expression, 4 times x minus 6 times the cosine. Now I'm going to check in a second here and just make sure that I'm in radian mode. It's the first time I've touched a trig button in this little session of using my calculator, so I just want to make sure. Pretty sure that it's in radian mode, but I'm going to double check. There we go. Right there. There it is. And sure enough, I'm in radian mode. '86. Graph of a function f here. Let h be the function defined by, so h is like the area from 0 to wherever. At what value of h attain its absolute maximum? Okay, absolute maximum, got to check endpoints. So I'm going to be checking the h function at -4, -3, and here, if I take the derivative of both sides of that, h prime is equal to f. So this graph of f that they gave me here, it might as well be a graph of h prime. So if I'm looking for a maximum, it's either going to happen at one of the endpoints or where h prime goes from positive to negative. So h prime goes from positive to negative right here at 0, and only at that place. So those are the contenders. So let's see. I need to know what is h of -4. That will be the area from 0 to negative 4. Notice that that's running the wrong way. That's going backwards under the F curve. So let's see. This area would be, each one of these triangles is a half, right? So there's 1, 2, 3. But sorry, this is, those would cancel out with those. So it'd be, the area would be negative 1, right? These would cancel out with those. So that area is negative 1, but this integral goes backwards. So it's positive 1 there. And then h of 0 is the area from 0 to 0. Don't need to do any more work there. That's 0. And then 3, from 0 to 3, that's all negative area going from 0 to 3, so it's some negative. That's definitely not the absolute maximum. Absolute maximum is at what value of x? It's at negative 4. But you see all of our choices are there, and then also where it has a minimum there. That's also included in the list. Now 86 is A. 87, position of a particle moving in the xy planes given by the parametric. This is the position. What's the speed of the particle at time 1.2? We just talked about that a minute ago, didn't we? It's the, I don't know why I keep putting parentheses like that. That is just not how you write that. It's that. Right, that's how you find the speed. So it's up to you how much you want to do by hand here. It's not hard to find these by hand. You want to make absolutely sure that you don't mess up the chain rule. Those would be the derivatives, and then we're going to plug in 1.2 into that. If you don't feel like doing that and you just want to go full-on calculator at this thing, you can just do, we want to find the derivative of this at 1.2, so you can do math 8, the derivative of e to the negative t at 1.2. And then same with this one. You can do it again, math 8. And then do this. You could just ditch the negative sign, or just be very careful and make sure you put it in parentheses. Probably better to just ditch it, in which case I wouldn't have needed those parentheses really. But oh well, I typed them in, so there they are. Same there, I didn't really need those. So 0.462 about. There it is, math. 88. The function defined by this for how many values of x in the open interval from here to here is the instantaneous rate of change of f equal to the average rate of change on that closed interval. How many times? Well, this is continuous, so we know by the mean value theorem it would have to happen at least once. So it's definitely not that. Now, since we have our calculator active, I think we can make this a pretty easy graphing problem. So the average rate of change on this interval is just that average slope. That's just f of 1.565 minus f of 0 over 1.565 minus 0. That's the average slope. Well, this is a mean value theorem question, right? It's just kind of in disguise. And I guess as long as you kind of make sense of what this is asking, you don't really need to know or remember mean value theorem. So that's the average slope. Go ahead and find that. So that's a matter of plugging, this is 0 and this is 0, so I just need to plug 1.565 into this thing here. You could just type it in, like 1/4, and then plug 1.565 and so on. I'm going to, because I don't want to keep typing that number in over and over again, I'm going to go ahead and store 1.565 as x. And then I can just type this expression in with the x's, and my calculator knows that that's what x is. So x to the 4th, oops, that's not how you do that, x to the 4th over 4 minus 2/3 x to the 3rd plus 1/2 x to the 2. Oh dear. Oh my. Messed that up. All right, 3rd, and then there we go. Plus 1/2. Took my eye off the ball there. Squared minus 1/2 x. Okay, so that should do it. So that's equal to negative 0.614. We did all that right. That looks good. Okay, now we want to figure out squared. I have a bad feeling that that's not right. Minus 1/2 x. No, that looks good. That is the average. Oh, sorry, I forgot to divide. That's why. I forgot to divide by that. Divided by 1.565. Negative 0.392. Okay, that is my average slope. Now I would like to know how many times that's equal to the instantaneous slope. Instantaneous slope is just the derivative of this. I think, I mean, there's ways of doing this with a calculator so you don't have to take the derivative by hand, but this is such an easy function to take the derivative of. That's x cubed minus 2x squared plus x minus 1/2. So I want to know how many times those two things are equal to each other on this interval. So I'm going to graph this, graph that on this interval, and just see how many times they intersect. Now, graph this constant. You could also put them both on the same side and then look for how many times they cross the x-axis. That's another way you could do that. X cubed minus 2x squared plus x minus 1/2. Ah, dang it. Do that again. X cubed minus 2x squared plus x minus 1/2. All right. I don't want to just graph this on any old interval. I want to graph it on that interval. 0 to 1.565. And that negative 1 to 1, that could work because that does have my horizontal line of at negative 0.392 in it. So let's try that. There's my horizontal line. We want to see how many times. 1, 2, 3, looks like. If you were not quite sure about this, you wanted to have a better look, you could just kind of zoom in around that line and do, I don't know, say, how about 0 to negative 0.5 for your y values? Negative 0.5 up to 0. I'll give you a little bit better look. 1, 2, 3. 88 is C. All right, 2 more. population of rabbits on a small island grows at a rate that is jointly proportional to the size of the rabbit population and the difference between the rabbit population and the carrying capacity. So they're not saying the words logistic differential equation, but that's what we're looking at here. If the carrying capacity of the population is 2,400, which of the following differential equations best models the growth rate of the rabbit populations with respect to time, where k is a constant? Okay, so the logistic differential equation looks like this. Some constant times p, and then 1 minus p over the, sometimes we use an A here, you could use capital L for the carrying capacity, or whatever you want to do, but that's the carrying capacity there. And it looks like, in the choices that they're giving us, well, let's distribute this out and see which one it could be. If you multiply, well, so this is the carrying capacity, so I should have just put the 2,400 in there, right? And you can see all of their versions have 2,400 as that constant. So this k, which we don't know yet, if I multiply by 2,400, I mean this k, which hasn't been solved for yet, that can just absorb the 2,400. It's just a new version of k, right? So if I multiply this whole expression by 2,400, then, so basically what I'm doing is this. I'm thinking about it like this. I'm multiplying this part of it by 2,400 and this part of it by 1 over 2,400. Or you can think of it as dividing that out, like factoring that out to the front. Either way, the moral of the story is the k, which we haven't solved for yet, it's just some other version of that k now. And this is 2,400 minus p. And so that gets us to our correct answer, D, there. Also, if you just really kind of literally take if you understand what the logistic factor does, like the closer you get to 2,400, the closer the slope gets to 0, I think you can kind of puzzle your way here also, as it's jointly proportional to the size of the rabbit population and the difference between the rabbit population and the carrying capacity. So that's really, this is the only one that does that. So, you know, you might be able to, except for this, which an Algebra 2 student wouldn't understand. In Algebra 2, you probably had the vocabulary to understand this part of it. There's your constant of proportionality, there's the population, and there's the difference between the population and the carrying capacity. So, pretty straightforward. Maybe that's easier than what I did here, but either way. Last one. Region bounded by 2 concentric circles. As shown, the radius of the outer circle is increasing at a constant rate of 2 inches per second. Radius of the inner circle is decreasing at a constant rate of 1 inch per second. What's the rate of change in square inches per second of the area of the region at the instant when r is 4 and little r is 3? Okay, so the area of that shaded region is pi r squared minus pi r squared, right? Outer circle minus inner circle. So if I take the derivative of that with respect to time, dA dt is equal to 2 pi big R dr dt minus 2 pi little r dr dt. This is related rates. This is back to section 3.7 if you need to review any of this. Formula from geometry, take the derivative with respect to time, and then plug in the stuff you got. So looking for the rate of change of the area, that's this. So I just need to plug in my stuff. 2 pi, when r is 4, dr dt is always 2 minus 2 pi when little r is 3, and dr dt is negative 1. So let's see, I got 16 pi plus 6 pi. That's 22 pi.